started. Welcome back. So let's see. So the lecture name will be in cross-validation and so p-values. But you you'd probably like me to talk a little bit about there's a but the midterm test is so it's going to be next week in class. All right, so it's going to be here when the class starts. So at that point I will hand out a test to everyone and you can get started. I'll just say a couple things. So I'll ask that all of you try not to sit next to someone. The room will be fairly crowded. And I think we have over half the seats in here, but there are a bunch of seats on the aisle, so see if we can't get anyone sitting next to us. So it's someone else. And you will be allowed one sheet of paper where you can write anything you want or print anything you want on the front and the back. And you can bring in but you cannot use a computer or a calculator or a phone. I'll ask you to put those in your bags underneath the desk. All right, thank you. Questions?
You said next week?
Oh, so sorry, tomorrow.
Yeah. Wednesday.
What?
Also tomorrow.
Yeah, so nothing. Okay. I don't know. These kind of days blend together now this time of year. Yeah, so it's next Wednesday, so in 2 days. Okay.
Wednesday the 4th of March.
So on Wednesday so Wednesday, March 4th in class. The next time there'd usually be a lecture, you're going to be here and you're going to be taking the test. Yeah. So March 4th is the only day of the year, which is also a May. Okay. So I'm going to be here to answer questions. The TAs will also be here. If you have a question on the exam when it's coming out, please raise your hand to ask the questions. If I see talking during the exam without me or one of the TAs around, I will have to assume you're cheating, and I will so I'll take your test on the spot. Okay, and you'll just get a 0. All right, so don't talk unless we're around. So I posted yesterday a practice exam. I linked to it on Canvas. It's also linked to right here on the web page. So the format and length of the exam should be an accurate reflection of like roughly what the exam should be. It might be a little bit longer or shorter, but it should roughly have 3 questions. They might not all be the same length. The points will be described on them. So if you understand those aspects of the course, those questions are not designed to be hard. They're kind of designed to kind of making sure you're kind of following following along the main concepts. Okay, so I think there were 3 topics on the practice exam. Those are pretty close to questions I've asked in the past. I try to give new questions every year. Some are going to be similar to ones from the past. Sometimes the questions are going to be different. Those are 3 topics. There are other topics the questions could be drawn from, right? So don't assume those are the only things you have to study, right? And it's everything up through the streaming section, not this lecture and the previous 2 on regression. I'm not planning on testing on that. That will go into the end-term exam. Yeah. So any questions on the exam overall, structure of it, and what to do? Yeah. Okay. Great. So then let's see. So the other thing which is coming up is the intermediate report for the class is due on Monday after break. It's so I think I have the deadline set at noon, so I want you to turn it on Canvas. The reason I want to make sure you print out a few copies, because in class on this day, I'm gonna give like half of a lecture, and then we're going to the last half an hour or so, we're going to kind of, I'll pair you up into, or triple you up into groups, where you'll discuss and give some, and you'll discuss and give peer feedback. It'll be a good chance to see roughly where other groups are. You'll get a sense of if you're kind of making good progress or not as well. And then, so that's why I want them done a little bit before class, so you make sure you have time to print them out and come and have some discussion. And then in this week, after the lecture, and then on Tuesday, I'll block a bunch of time, and a bunch of time on Wednesday, we're going to schedule some, every group will schedule a meeting with me. Okay, it's gonna take place in my office. We're still working out the schedule, how to do this. It should be announced like some point in like the middle of this week. And I think each group will get like 7 minutes, so something like that. And so try and do it to 7 minutes, but there'll be breaks because some groups will run kind of slightly long, so I can catch up. I think I've got about like 9 hours of meetings over these few days with all the groups. So we'll try and get through them. There are 53 groups this year. When you come into this meeting, you should have printed out your project proposal, your day collection report, and the actual intermediate report. And when you come into the office, you'll hand those to me, and I'll kind of read through them and give you feedback in this kind of short time frame. For most groups, this is a good amount of time. For a few groups, we can there'll be more things to discuss, and we can schedule some time after that as well. But the point is, you should try and get it to a state where you can kind of see if what you're doing is kind of like roughly working, and you have a sense of how it's going, and I can give you specific feedback on what you should do to finish the project. All right, so if you haven't done very much, then I won't be able to give you a lot of feedback. Okay, so don't worry too much about kind of being super precise, and I mean like everything finely detailed and carefully written in like the intermediate report. Make it so I can read through it quickly, but the point is not like a final report. It's you put in what you've done so far, and I can give you feedback on what you plan to do. All right, so that'll be after we get back. So any questions on that before we get going? Great. So now we'll start the lecture, and we'll start with cross-validation. Then I'll talk some about p-values, and then hopefully we'll get into more of a discussion at the end, because this is stuff where I can tell you some sort of techniques, but there's a lot of kind of like these like gray areas and these nuanced cases, and so I think it's more useful to have a discussion. Okay. Great. So how many people have like heard of p-values before? How many people have heard of cross-validation before? Good. So let me still explain it, and maybe I'll explain from my perspective, which might be a bit different, and we'll move through it and talk about some variants of it and some pitfalls of these things, right? So cross-validation. So the idea is, there are like two things this accomplishes. So how to choose, so like how to choose parameters, and generalization. Right? So what this is doing is, so I like this teaches after regression because this is kind of the simplest place you can actually use it properly. So you need some sort of, a cost function, C, which is going to take in your data, and so then your model, and your model will probably have some parameter. All right, and so the example of this would be the cost function on x, y, if on like regression, and this is the model, and so then it would be kind of sum over I equals 1 to n of yi minus the model of s, or some model based s of xi squared plus s times, let's say this. All right, so let's write this slightly differently here. Let's say this is some model and then some parameter. So, okay, so then it'll be like alpha xi. So this is the some linear model that you have here. Okay, it doesn't have to be linear. And then you have some like regularization parameter at the end, which says how much to weigh these two terms, right? And so this S is something that and we had talked about before had to be given. But one of the things that cross-validation can be used for is going to be like how to choose this parameter, right? So what the basic idea is that you're going to have some data set X that's, say this is X, and so like this is Y, and we're going to split this data set into a training set. We'll call this training set R, and so like a test set S. Okay, and so what I'm going to do is I'm going to randomly select a subset of these rows, and it's going to pair it with the Y value, and it's going to put them into this training set. So this will have some Y value in the training set as well, and then also in the test set, and then the ones which are not chosen in the training set are going to be going so like into the test set. Okay, so I'm randomly splitting my full data set into a training set and like a test set, and then I'm going to I'm going to split x, y into R and S. I'm going to build some models, alpha S1 on so like in the case of regression, this can be R transpose R plus S1 I inverse R transpose so YR, and I can so then I can repeat this with like different choices of this parameter S, right? And then I'm going to evaluate the so the models on like the test set. So I'm going to get a cost of S1 is going to be evaluated as like the sum of I equals 1 to Rn or and R, right? So just the ones, sorry, just the ones in the so like in the test set. Here, let me write this a little bit clearer. So let's say xi in S of yi minus xi alpha S1 squared. Right, so I'm going to compute the cost function just using the ones in the test set, and so then the parameter I choose, then I'll choose the parameter to build the model with just the ones that does best on on the test set which has been held out of the training process, right? So I've randomly split the data. So I'm only using the training data in this step to build the models and only using the test data to do the evaluation. Yeah.
On the right-hand side of the first model, that's just the closed form solution of regression. Is that?
Yeah, but I can, I wrote it as an explicit example here because we have a closed form solution in the, so like in the case of rigid regression, but what you could do instead is you're going to actually run some algorithm at this step. It could be some version of like gradient descent. You know, it could be least single regression in, so like in the case of like the Lasso formulation, right? But this is some algorithm to try and solve for the model, right? And so another example of a parameter, if I'm just looking at the sum of squared errors, so I'm not adding this like ridge term here, and I'm using gradient descent to solve for it, for instance, the parameter might be the number of steps of gradient descent I run, right? This is a parameter I can put in, or what is the stopping condition on gradient descent? When do I think I'm close enough to the right algorithm? That's another parameter that goes into building these models, right? In this case here, we have this very clean parameter. It's very obvious. It shows up exactly in this cost formulation, okay? But, you know, you often don't need to use that in the actual evaluation, right? I want to evaluate it on how well it actually predicts this data, not necessarily on kind of this biased version of predicting this data which is held out, this test data. Right. So then, you know, at the end of this, I say, you know, this S1 parameter or S3 parameter gives me the lowest cost function. Then I would use the associated so model here, right? Would then be my choice of the model I've learned. Right. So sure. Okay. So why does cross-validation make sense? Right. So why does it make sense to do it this way? Right. So we'll talk later in this lecture about p-values, which is kind of an old way of thinking about evaluating. So like if your model is correct. So the like rationale behind this is that you have some some, let's say, unknown, so, so like there's some like, there's like some unknown distribution, right? And and we've kind of assumed, and this is kind of under the hood, I haven't completely unraveled every part of this in this course, but that you're making these observations x, y, which are coming from some identical and these and like these independent samples from you, right? So I'm collecting customers into my database of how they interacted with my website, or they've made some recommendations of like these movies, or they're kind of these different documents making up this portfolio of like documents over the web, and I'm trying to kind of maybe crawl the web, but I haven't crawled everything, but I'm assuming that I have enough of them that it's a good distribution. And there's this baked in underlying assumption that these are coming identically from the same underlying distribution that I'm trying to understand, and that that these are independent of each other, right? This is probably not exactly true. There's probably always going to be some correlation in between your data points, but it's like this is hopefully some reasonable thing to assume. It's like not too far off. There's some places within like statistics where this is important. For instance, I'm taking some measurements of like a time series, and things tend to kind of, the time is then important, and the two measurements might be pretty similar to each other. The finer my resolution, the more similar the measurements are going to be to each other, just because some sort of phenomena I'm measuring can't change too much over time. But so you can measure, you can sometimes quantify, so something called the autocorrelation, about how similar is something to its neighbors in the sequence, or maybe there's some spatial components, spatial neighbors. And usually what this tells you is that they're not completely independent, but it might allow me to say, well, if I effectively separated the samples far enough, they're going to act like they're independent. Okay? And so this is not an exact description of what's going on, but even when there is some correlation, it's often saying if your sample is large enough that it might not act in a central limit theorem fashion where you get convergence at the rate as all n samples, but it's something like n divided by 2 or n divided by 3. So even with some non-independence, this is usually not like too far off from like a actual true assumption of what's going on, right? And so then, kind of, we think of what the next step is. I'm splitting this into the training set and so the test set here, okay, and so this split is is also going to occur at random, okay. So then what this means is that if this is random, then this sample and this sample are both going to be like I can think of both of these samples individually as like also being IID from this unknown distribution, right? So it means that the model which is coming out of here, so this one is a model. This model is also basically trained from some IID sample from the underlying distribution, and this evaluation of the cost, right? This evaluation is also based on some large enough sample from this underlying distribution. So it's saying You know, if I were to draw new data, then this evaluation is kind of a prediction of how well I would do on this new data that I haven't seen yet when I'm training the model. Yeah.
So this is great, helping us get to the parameters that we need, but how do we choose the size of the test or the training?
Sure, yeah, yeah. So great question. So like, what should the train test split be? Right. So some common ones are like 70%, so 30%, 90%, 10%. So it can even be like 99%, like 1%. So this depends on how much. Really depends on how much stake you want into trying to build the best model versus how accurate you want the evaluation to be, right? And so if you really, there's like, as you get, like as you get like more, data, you can build like a more complex model, right? So you can probably like reliably build if you're doing like polynomial regression, you can reliably build a higher degree polynomial model if you have more data. Whereas if you don't have a lot of data, you probably don't want to try and increase the degree of the polynomial. If you don't have a lot, you probably just want to make like a linear model. Whereas as like the part with the evaluation, so this is evaluating a like this is evaluating a like single scalar cost function, right? So the single scalar cost function is going to converge towards its mean, right? And you're trying to use some sample estimate of this mean to like evaluate so like how well this model works, right? So the part with the testing part does not really need to grow that much as you get more and more data. If you're evaluating lots and lots of models, it's going to grow with the number of models, but so like if you're evaluating lots and lots of parameters, you need to ensure each of those estimates are accurate, but this doesn't quite grow as fast as potentially how complex the model you want to get is. So I would typically, instead of thinking about what the split should be, I would aim for the size of the like the size of the test set to be about something like 1,000, and so I would say, and like I would say more if you are like evaluating a lot of parameters. So if you're just evaluating a small number of parameters, probably around something like 1,000 is going to give you like a pretty good estimate, up to like you know you could probably apply like a Chernoff-Hofting bound on this, and if you have a bound on the accuracy, for instance, let's say the accuracy you're estimating kind of values between 0 and 1, you should be able to kind of roughly feel comfortable. So around like 2 or 3% error with like 1,000 samples. Okay, you know, 2 or 3% error probably is like smaller than the amount of error you're putting in because of modeling or because of other sort of uncertainties you have. There are certain tasks which people have deemed like very important, and so there are lots of people competing on these same tasks, trying lots of different models on these sort of things, and then they often want the evaluation set to be much larger because there's going to be effectively a lot of people trying different parameters on here. And they may want to distinguish between different levels of accuracy. Between 70 and 72% might actually be a big improvement, but you might not be able to really reliably say that at like 1,000. So at that stage, you want to have even larger for the evaluation set. But in most cases, kind of around 1,000 is going to give you roughly a pretty good estimate. And then you can often put the rest into the training set. So that's why this test train split is not necessarily the best way of thinking about it. Okay. One of the other things this says is that, well, I want to put, let's say roughly 1,000 into this testing set in order to really trust it. Okay, if I'm doing that and I only have like 500 data points, well, then I can't put 1,000 in here, and if I did even put half of that many into there, I would have nothing left to train my data on. And roughly, right, so it's just not going to work, right? And you know, even if I get this, I'm at this like 70-30 split, you know, if I put 1,000 in here, I want to have at least 2,000 some left over to put inside the training set, right? This is usually on the low side, but you know, it's not uncommon in many cases. This really makes sense when like data is plentiful. Okay, so if you don't have a lot of data, or it's like you think you have a fair amount, you can still use this, but you shouldn't be able to trust it as much. Your evaluation, you know, is only going to be as good as like the size of the test set and the variance in the actual results, right? If the variance in the results is pretty small, right, then if you look at applying like one of these like Chebyshev bounds, which directly uses the variance, or Update bounds can be a bit stronger if you have kind of a stronger bound on what they can take. And if that range is small, then you know, I'm going to converge to a higher accuracy more quickly. And maybe I only need like 100 samples, or I can do something with only like only like 10 or 15, right? So like this idea of like traditional statistics and p-values dates back to like 100 years. People weren't doing this 100 years ago because they didn't have data sets that were this large, right? So this is much more of a modern way of thinking about it, because it made sense when we had large enough data sets where we could spare some to put in this evaluation set. Okay, and with those in the evaluation set, we had enough to really concentrate to get a good estimate of how well these different parameters were actually working. Yeah.
Do you know of any examples where the test set is a larger percentage than the training set?
I don't know of any offhand. It's possible that you could do that, right? But it would be usually the test set is smaller.
So what factors play into choosing the cost function for the evaluation?
Yeah, so that's also a good question. It's like mostly beyond the scope of this class. So, you know, most of what we'll talk about is just using like the sum of squared errors. There's like a way you can drive that for a lot of cases from thinking of your observations, which are measuring. So they have like a normal distribution, and then you end up trying to minimizing the negative log likelihood. If you write down it probabilistically, you can think of doing that. And if they come from a normal distribution, then the model which minimizes the negative log likelihood is the thing that minimizes the sum of the squared errors. So there's a derivation, you can get that. And in regression, this is by far the most common way to measure error. In classification, which is another thing we won't talk much about in this course, they also have this labeled data where they have kind of these explanatory variables x and some labeled data y, which is then typically a class. Then there are a more diverse set of ways to actually measure the error. And there's kind of an industry of developing these different ways. They're all typically proxy functions for the number of misclassifications you made, and that turns out to be harder to deal with. So, you could choose, you could say, I think if my data has like Laplacian error on it instead, and then you would want to minimize the sum of the absolute value of the residuals, not the squared residuals. And that'd be a quite reasonable thing to do if you thought you had Laplace error. You could use a different cost function instead, and that's probably also fine. They're probably going to give you, in most cases, pretty similar results. They differ in how they deal with noise, right? For instance, the sum squared errors is susceptible to noise. So if I think it comes from Gaussian noise plus outliers, then I might actually want to use the sum of this absolute value of the residuals, because that's going to be more resilient to these outliers instead. Or I could say I would want to measure the fraction of the data which is within some absolute distance of my answer. I only care if it's within 0.1 error, whatever 0.1 is some parameter. I say that's good, otherwise it's bad, right? And so you can use a cost function like this as well, which is a discrete cost function, but it should work. It should work fine, right? So you can use all these different things. So great. So if you want to do, let's say cross validation on small data. So you can say maybe artisanal data. So you have a small but handcrafted kind of set data you think is very representative. I have this, I don't have a lot of data, but I trust the data I have. You can still use cross-validation on this. But you're not going to want to spare everything into the test set, right? So let's say that so the size of data n equals like 20, right? I don't want to use I want to still run regression, and I still want to evaluate how I'm doing. There are these other things like these R-squared measures, which tell you something else about the data, but don't directly tell you about how well it's going to work on like new data. Then what's difficult to do is leave one out, or LOO. So cross-validation, and so what this does is it splits n so different ways. So I have the training set R1 is going to be equal to kind of x2, x3 up to xn, and Ri in general is going to be x1, x2 up to xi minus 1, xi plus 1 up to xn. And then each of these is going to be paired with the test set, which is going to be just x1. case, just xi. This is x1. Right, so now the test set is going to be a single object, and the train set is going to be everything else. But I've done this n different of these splits, okay? And so so now the procedure is going to be slightly different. So now I'm going to have one is I'm going to split into these n different ways. Two, I'm going to build n models, say alpha 1, which is basically a train on R1 and so y of R. So y of R1, and alpha I is going to be the train on Ri and y of like Ri, right? So I'm building these n different models here, and I do this for every parameter choice, right? So this also depends on some parameter s, right? And so then I want to eval the data. So I compute the cost function on S1 with the model alpha 1, right? But I want to do something like I want to take the average over the cost function on all like all of these, right? So to evaluate a parameter, I'm going to evaluate on this model. Each model I built on the training set for all the data except for one point I held out, and then I'm going to test on this one value here, right? So now I'm building. I'm using basically every time I build a model, I'm basically using all of my training data except for one data point, but I'm evaluating on all of the training points as well. Okay, so I still have this split separation between the training and the testing, so I'm not having my model is now allowed to know the data point is there and go through it, but I can still evaluate on like all of my model. Okay, and this is important for small data because I'm using all the data, but it's not very good on big data because I have to build n different models, right? The evaluation isn't so bad. I'm still only evaluating on n data points, but I'm building n different models, and this would be really slow on big data. So this works well on these small data sets. And then on intermediate data sets, I can kind of go in between. I can do a test train, 10 different test train splits where I say hold out 10% of the data, build on 90%, and then repeat this for every 10%, right? And so this is kind of how you interpolate with medium-sized data. And this works, you know, this works okay. If this is too expensive, then I can do some kind of smaller number of splits, but larger number of test sets, and I'm going to get even more accuracy, right? Yeah, so what's complicated about this is then, okay, so now I've built this, I've done this and I've chosen a parameter. Now which model do I use? I've built these n different models here, right? So which one do I want to choose one of them, right? Right, so I want to choose one of these models. Okay, so let me, so if I choose one of the models that I've already built, well, I'd have to choose one of those. So I've heard some kind of various answers on this. So I can do something like choose the param s that's smallest, then read rebuild on all of X, Y, right? So one thing, I could rebuild, redo a retraining on all of the data once I've chosen this like parameter S. So doing something like this on small data is probably not too bad. I could also just choose one of these. The idea would be that these would probably be pretty accurate representations anyways. There's only missing just one of the data points. What you should not do is to choose the one of these which is doing the best. Right? I'm going to look at the average of these, and I should not choose one of these which is doing the best. I could choose one kind of like at random, but if I choose the one that's doing the best, this is like biased in a strange way. Okay, it's biased towards doing well on that data and the data point I've chosen to held out, and I shouldn't expect that one to do better on new data. I'm probably better off choosing one of these at random instead.
Oh, what if you were to just take the average of all of those as the...
Average of the models.
Yeah.
Yeah, so taking the average of models doesn't necessarily make sense, right? So if you just think of like linear regression in the plane, you have two parameters. You have the intercept and you have the rise over run, the slope parameter. And I'm taking the average of all the slopes and average of all the intercepts. That it could mean that there are two classes of models which do well. There are kind of two modes in the space of models, and taking the average might wind up in between those somehow. You know, this maybe does not happen in like in a regression, but in general, this might be something that happens, right? So I don't want to I don't want to blindly ask you to do this because you might get some strange effects that way, right? There could also, I mean, this is especially true as you get to these more complex models. What's happening kind of common in practice nowadays in large scale or regression is you're doing something like these deep neural nets, or if you're doing like one of these models for like lasso, for instance, the models might be sparse, but they might be sparse in different spots, right? And so if you so with lasso, you're going to increase the density when you do that, which isn't necessarily good, right? When you're doing with these deep neural nets and other of these very overparameterized models, what's going to happen is they're overparameterized, so there's lots of symmetry in the space of solutions. So I can have two models which are basically symmetric to each other. I can have two roles and two variables which you could replace one with the other. When I'm averaging them, I'm not doing either of those things, right? So there's more complex things going on, and blindly averaging them might lead to some strange results which might perform strictly worse than before. So there might be something you can do in linear regression. You know, I'm not aware of these arguments of why this could work, but in more complex models, this can definitely cause problems. There.
So you said that you shouldn't choose like the best model from all of your different splits because it might be biased. Is that just in the case where you only have one test variable? Because say that you have, you have your training with larger test inside or validation inside of that. So say you have 10 splits inside of it, or just 10 splits in general. Would it make sense to choose the best S for that because it's kind of assumption is you're sampling more from
Yeah.
each of the
So I'm building lots of different models here. I'm building one model. I'm building n models for each parameter, right? Then I'll have another parameter I might be evaluating over here, right? And I'll choose the best parameter that way, right? But then choosing the best model out of this way, if I choose the best model, I'm more likely going to accidentally seep into some strange, like, adversarial case. If I picked one at random, less likely to do that.
Okay, so you said you choose the best parameter, meaning S in this case.
Yes, I'm correct.
Okay.
So I want to choose the best parameter S, and then I want to choose, so there's S1, there's S2, and I want to choose one of the models built using S1, if S1 does the best on the average. Okay? But then which model I choose, I don't want to necessarily average them. That might lead to some weird things. I don't necessarily want to choose the minimum in terms of the cost function, right? Because I'm only evaluating that minimum on a single data point. I don't trust that too much. And it's more likely that choosing the minimum is going to be one of the extreme cases over the distribution. It's more likely that there's something weird going on. Like in linear regression, this might end up being okay, but in more, I don't want to, you're usually going to be using these in scenarios that you have less understanding of what the underlying model is doing, and that's more likely getting you into just one of the extreme cases instead of an average case, which is what you want to trust. So I would just pick one at random. If it happens to be the minimum one, just live with it, right? But I wouldn't intentionally bias towards the one of these that best fits the one held out data point.
Why would you not simply rebuild the model using all the training data points?
Yeah, so I mean, on small data, this is probably okay. This is kind of like on large data, what you're doing is then you're kind of mixing this choice of parameter back into the training procedure. And so you could probably do that, but you're kind of like, you kind of want to keep these like separate. How well you think you will do on this model will probably be an overestimate. But this is not necessarily a bad thing to do, but this is not generally what's recommended. I mean, the recommended, this makes sense in the case where you have one test and training split, and then you just use the one just built on the training data. And so this is not doing that when you have these multiple splits. Yeah. So I want to say something else. So and this is similar to a bunch of the questions that you guys are asking. But so there are these two uses, right? There's to choose the parameters, and there's to evaluate the model, right? And so what we've talked about so far, this is what we've talked about, to choose the parameter. What we've done should not be used, how well we've done on that test data should not be used to evaluate how well we predict the model will do on like new data. We go back to this picture here, we're supposedly getting this IID sample that comes out, and we're evaluating, and if we take the average over those, that's kind of a representation. If we got one average new point, how much squared error, or whatever our cost function is measuring, should we expect to get on this new point? We want on average that to be small. But if we use that for the evaluation, it's slightly biased because we chose the value, the model parameter, which did best on this test set. Okay, so if you want to do both of these things, okay, so if you want to do both, then what you should do is you should split. So then you should split like 3 ways. You should split your data set into the into R for the training, into S for the test of and like the test of the parameter, and to E to evaluate the Okay, so if I want to see how well this will do on the new data, what I'll do is I'll build a bunch of models, train them on the training set R, then I will choose the best parameter using S, and then if I want to know how well to expect this to do in the new data, I should use a separate training set E. Okay, and this seems like I already have a pretty good evaluation. Why do I need this? So kind of this like separate set. Well, what's happened is like people have so there are like these online these like online contests, like things like Kaggle has like if people heard of Kaggle. Yeah, so this is the thing, and what they'll often do is they'll give you some public version of the data, and then they'll accept a test of you build a model and you evaluate it on some test data, and they'll maybe only allow you to do this some limited number of times, like once a day, and there are various models that different testing things have like set up. They allow you to evaluate, test a day, how well your model with your parameter works. You can do anything inside of the training data to test your own parameters, but if you want to evaluate how well it does, they give you that S once a day, and then at the end, they'll evaluate it on a, this will give you like a leaderboard just on S. That's the publicly available one. But if they do this properly, they should hold up a third set that the final evaluation is done. Okay, and the reason that this is important is because some people figured out that you could basically throw random models at the test set, and then you can use techniques from machine learning like boosting, which are complex forms of like averaging the models in a sophisticated way, that allow you to do really well on the test set without having looked at the training set at all. Or maybe looking at it just kind of without really inspecting it. So I'm not really learning something, I'm just trying to fit the test set. And then they will do basically average on a third set, which is held out. Okay, so people have demonstrated this in these contests, and so if you don't keep this third set, you can try lots and lots of parameters and overfit onto the test set, and so it will not be a representation for evaluating how well you do on future data. Okay, so if you keep trying these parameters over and over again, then, which is common in like you're trying to build a system, you're trying lots of different ways to kind of build a model for it, or it's a known problem like one of these, like this CFAR data set used in kind of in computer vision and deep nets where everyone's trying to do well on this, that they optimize to the actual test set. More so than they would if there was new data from the same distribution. Right, so you want to hold out this third data and only use this at the end, and then you can't keep running the contest afterwards, right? If you want to have a true evaluation, unless you have a fourth data set that's held out. Okay, so there's reason to kind of keep these tasks separate from each other. And if you have lots and lots of data, you know, millions of data points, I can spare 2,000 instead of 1,000 points to hold out, right? Or even more than that, and still have a reliable set to do all the training. Okay, great. So this is kind of most of what I want to say in cross-validation. I want to spend the rest of the time talking about these, so like p-values and such. Okay, and so p-values are this kind of this different way of like trying to evaluate a model, but it's built on a different kind of underlying understanding of what's going on here. You're trying to say that there's some underlying assumption about the world, about some sort of so this is like the world's hypothesis, and we'll call this H0 that is generally accepted as true, and so then you want to make some H1, so some H1 hypothesis, which you think might be a better explanation of the data, okay? And so you want to say, is there an H1 hypothesis which could be a much better explanation of the data? And so the way this is typically done is you assume that the data, in order for this to work, there needs to be a very kind of specific model of where you think the data is coming from. Typically in data mining, we think much more generally, it's just some distribution. We're trying to fit some class of models, how well can we do? Saying, I really think I know it's this type of Gaussian, something like that. Could be different distributions, but, and then if I look at the data, and I can write down often the likelihood of that data. I assume it's Gaussian noise, I make these, if I assume independent observations, I can take the product of all those, of like all those likelihoods. If I know enough about it, I can normalize, I get a probability out, and if the probability of that observation is kind of very unlikely, meaning that or something more extreme is less than some probability, given all these assumptions, then I say that the p-value is this value. The probability that this occurs or something even more different than my underlying null hypothesis about the world, and then you'd often propose some H1 hypothesis as being, let's consider this instead, because if the p-value is very small, the probability of seeing something more extreme than the data is very small. I would say with this, some confidence, 1 minus this probability confidence, I would then try and reject this null hypothesis. If you see data that actually is in the middle part of the curve, so there's quite likely to be something more extreme, you don't accept the true hypothesis. You just say the data did not say it was unlikely. It doesn't mean there's another model which is more likely. It's just kind of ruling these things out. Okay, so it's kind of a different sort of approach, but this was kind of these picking one very rigid model and then potentially replacing it with another very rigid model is a lot of how science and statistics has worked for like the last 100 years or so. Okay. All right, and there's a lot of ways. If you notice, like my explanation was not some single clean mathematical formula, and I had to say about several paragraphs of description. It's kind of it's kind of a nuanced sort of definition, and this has led to some issues in that there are ways you can get the nuance wrong, and you can make false kind of decisions about certain things or unfounded decisions based on data. So I want to talk about one of these possible issues. So so how many people read XKCD comic? Yeah. So how many people have seen this comic before? Yeah. So a few of you have. So there's this one thing called the multiple hypothesis testing. And that's the idea that in modern science, that people are trying to propose lots of hypotheses of what is going on. And this is not too different from what we're doing in like this regression model as well. But like this is more clear within the multiple hypothesis testing within the p-value framework. Okay, and so how this could go, this is an illustration in this cartoon, is that so these scientist has a hypothesis that jelly beans cause acne, and he says, well, they investigate, and they say, well, we didn't find a link, and so we couldn't reject the hypothesis that they don't because the p-value is greater than 0.5, right? So they say, well, but I hear it's only a certain color that causes it. Maybe like red 5 is a weird food coloring. So let's test a bunch of these colors. Let's test purple jelly beans. No, there's no link with purple jelly beans. It's above 0.5. Brown jelly beans, it's greater than 0.5. With pink jelly beans, greater than 0.5. And you can run this, say 20 times with different colors. And And if you notice on here, in one of them, right, one of them, the green jelly beans, it's less than 0.5 probability that this happened, and so they write a paper, it makes the news. Green jelly beans are still linked to acne here, right? So what's happened here is that I've run 20 trials, so the probability that I would have observed data that was in the 5% extreme happens roughly 1 out of 20 times. I've run 20 trials, so it's not unexpected that one of them would happen at an extreme of less than 5% of the time, which is what has happened in this example here, right? But there's been a lot of kind of science which is operated essentially under this model, right? Where there's some type of cancer people want to understand, a lot of different labs try something, and if they all try even the same experiment 20 times, one of them might make observations which would occur less than, 5% or less of the time. That would not be unexpected, and then they would publish a paper. Okay, and so kind of within some kind of data framework, like there was like there's this paper that came out in 2005, and there's been follow-ups to this that showed that most published scientific research findings are actually wrong. Because of this, these really exciting things that a lot of people tried to do and failed, they tend to get into these top journals. Because they're like, oh, this is a breakthrough, right? People have been trying to do this for a long time, but maybe it was just because of this kind of, this multiple hypothesis testing, right? And so this led to kind of around this time, there was this crisis of science around p-values. There's this like Bonferroni correction you can do where you say, well, I'm going to calculate log all of my planned hypotheses I've done, and then the p-value has to be even smaller. I can correct for what the p-value should be because of all the hypotheses I've tested before. But this doesn't really fix it. You could have done some data sort of manipulation, and this could still cause this error. There's all these intermediate steps which are going on in how I'm processing the data. I look at it in between, and that's guiding how I do my experiments. And it's hard to correct for all these things. This is, I think, has helped, but I don't think people believe this has solved the problem entirely.
So what's the difference between, which one is better, P1 versus, F1 versus P-value? The F1 score.
The cross validation or p-values or
No, F1 scores.
F1 scores. Oh, I always get confused about these different names for measuring error. There are ways you can fix the type of false negatives and then minimize false positives, or you can add these things together in some way. And these are okay. This is effectively just a different form of a cost function that you're using, and you can use cross validation around this cost function instead. Whether I think the F1 score is some combination of false negatives and false positives, and that's more of a classification sort of measure than for regression. So we don't get into it in this class just because we pushed the classification stuff into the machine learning class. But I mean, it's not a solution by itself though. It's just a cost function which is a proxy potentially for what you want to do, and it can still have issues with contamination of data in how you're evaluating a different problems. Yeah.
So is Bonferroni doing, is it just changing the p-value like threshold depending on how many variables you're looking at? Is that
Or like how many hypotheses you've tested,
Right,
or how many
hypothesis, right.
parameters you've tried,
Gotcha.
basically.
Changing the p-value.
Yeah. There are other more sophisticated ways which are more complicated. Like there's the most standard technique is actually this technique by like Benjamini and like Hochberg, where you need to run lots of experiments, and then you kind of see what happens at the tail end of these, and it's more. But there are other mechanisms for this, and you can at least understand empirically where you're getting these false positives under all the different hypotheses you've tested. But it's not necessarily a solution to all these things completely by itself. All right, so I want to mention the last 10 minutes. I want to mention this there's this paper by Andrew Gelman and Eric Loca in 2003, which I think kind of really pinpoints what the kind of clarifies one way of viewing this issue, which I think is subtle, and until you see this, you may not grasp how potentially severe this issue is, right? So kind of the classic hypothesis test is you have, you're basically collecting the data for the experiment you're doing. And then you throw that data away. You can't use it for anything else, right? You have a hypothesis, then you collect the data, then you evaluate it, then you throw the data away. You can't use it for anything else, right? So this is how you're supposed to do it and how really old statistics work, right? There's the other version of this, which, the extreme of this, what you don't want to do is like, so like this fishing, where you kind of try a lot of these different hypotheses or maybe these different parameters, and if I'm evaluating on actual data, I'm just going to find one which is the best and report this one as if this is the only thing I ran. Right? So if I try enough hypotheses of like the green jelly bean thing, I'm going to eventually find something which, if I just look at that part, it looks like it's significant, but if I look at the context, I can't do that, right? Doing this on purpose is called fishing, and it's bad. You shouldn't do that. That's kind of acceptable. Okay? But there are things in between here, and understanding where these go is kind of important. And these are text directly from the paper. So then there's the planned correction of this, which has come out of this kind of crisis, was that you pre-choose all the set of experiments you're going to run. I'm going to test these hypotheses or these parameters, and I'm going to kind of evaluate that properly. I'm going to document it so in a database, so other people want to test the same thing, they can account for this in their analysis as well. Right? And so doing something like this should generally be okay, right? But this is probably not what most people do. They probably do this third thing that fits inside of here, okay, where they call it researcher degrees of freedom without fishing, where I kind of choose what tests to run after I've kind of looked at the data. I take the data, I do exploratory data analysis. I take it and everything you learned in the information visualization class that says you maybe shouldn't do that, because what you're doing, you're looking at it, I'm plotting it, I'm running clustering first to see if there are clusters before I try and build how complex my model should be. I'm sort of using this exploratory techniques before I choose my hypothesis or before I kind of list the parameters I'm going to try kind of in building some model which is actually predictive that I have a cost function over. Okay? If you do this, this is basically, it's the same problem as with fishing, but it looks a lot like 2. Okay, and so 2, if you do 2 properly, it should be okay, assuming the whole community is taking this accounted for. But people are often doing 3. Okay, and some of the techniques I'm telling you in this class make it easier to do step 3 here. Okay, but right, so I think within data mining and machine learning, often people are actually doing 4, and they're just, not totally, if you run too many experiments on the same evaluation set, you're basically doing some version of 4, not framed in the p-value way, but you're effectively doing that. You're overfitting onto the test set. Okay, it's this same sort of badness as doing 4, but even 3, if you think you're doing okay, but I've kind of looked at the data to try and decide what evaluation to run, I'm kind of running into this pitfall. Okay. Yeah. So this this paper does not offer any like actual like perfect solutions to this problem. They say, well, you can do 2 and that's fine. You shouldn't do 3, but you know, it's very tempting to plot your data or to look at a few data points before you start running analysis, right? That seems like part of the pipeline we like should be doing. Yeah.
So I guess then, like, at least in the case of like our projects for this course, like I took a lot of time literally just plotting it over and over again because I didn't know what any of it was.
Yeah.
So I guess how do you resolve this tension between you need to understand what your data is, but also you can't understand it too much, otherwise it's going to bias the way that you propose your hypotheses.
Yeah. So if you properly do cross-validation, it actually covers up a lot of sins. Okay. So if you had, before you did that, you had held out some of the data, then all that inspection and looking at it and figuring out what to do is actually going to just go into the first step, into the training part, right? And maybe you split that held out set into 2 parts, one where I choose parameters and one where I do the final evaluation. If you've done that already, maybe you can collect new data. You know, it's kind of a challenge. I think most people still, even after this article came out, which a lot of people read, most people don't properly do it. You know, so in this way, okay. Like if you end up choosing the right basic model of where the data comes from, it's probably not as much of a sin. You might be getting the right answer still, but you've kind of mixed up your evaluation with your building of the model. Is what you've done. Sorry to tell you this if you've gotten too far ahead of your projects, but you know, at this point in the projects, I hope you will just kind of like try and recognize you've done this and state it clearly, as opposed to kind of throwing everything up and say I have to start over from scratch again. I mean, there's definitely some kind of, when you're doing something like this, you're definitely mixing the evaluation into the actual modeling part. It's pretty common. This is how most progress gets made. And a lot of times you will eventually be able to get new data, and then you can predict on the new data. You say, I could get around with saying, let's say this is some data which is being collected from the wild. Eventually there'll be new data. I can go back and predict it on the data that comes out after this project is done or the paper is published, right? And so in the long run of science, this often gets resolved. People will try and replicate experiments, and if it doesn't work, then there'll have to be retractions. Sometimes these are painful, but this happens. If you make a prediction and you think you've mixed up your training with your evaluation, well, if more data comes out later and that turns out to be a useful prediction on the data that came out after your analysis, your model is built, then that's great. If not, then someone will try to fix it, right? So this kind of comes out on the fly and is self-correcting in the long term, but in the short term, this can lead to some problems. And there's like these feedback loops where these labs will get a lot more funding to continue work on something. It could be millions of dollars within kind of science, and that's more of one of the worst consequences. Well, that and like pharmaceutical drugs which maybe kill people, that's probably worse. Yeah, so there are various consequences that come out of this, yeah.
Does like doing meta-analysis, seems like that's kind of like also trying to solve the same problem, or does that not, do meta-analysis not help?
Yeah, these meta-analysis are more diagnosing this problem, And if you do properly with 2, they can aggregate together a bunch of these studies and correct for, say, what the p-value is, or maybe they get new data to evaluate it on, right? So a lot of, in data mining, what often happens is someone says, I took this new data set and I re-implemented all these algorithms and I saw how they work, and this is what my observation is of someone who doesn't have a stake in any one of them. And that sort of study is very useful, right? And so if you do that properly, that works really well. So great, so we'll stop here. I'll see you all on Wednesday. In 2 days, there'll be a test, not next week, not tomorrow, Wednesday in class.